we'll discuss LU factorizations. And a factorization of a matrix is when we write it as the product of matrices. Just like if we factor a polynomial, we write it as the product of other polynomials. Here we're going to write a matrix as the product of matrices. We assume we start with an m by n matrix A, and we're going to write it in terms of what is called the LU factorization. L will be an m by m lower triangular matrix with 1s on the diagonal, and here in a minute we'll define properly what a lower triangular matrix is. U will be an m by n row echelon form of A that is found using only row replacement operations. So we will be very strict on which operations are used to find this particular row echelon form. We will now properly define a lower triangular matrix. A lower triangular matrix is a square matrix with zeros above the main diagonal. So one example, 1, 0, 0, 2, 3, 0, 4, 5, 6. Here we can see our main diagonal. We see that everything above that is a 0, so this is lower triangular. In particular, because all of our non-zero entries are in this triangle that's at the bottom of the matrix. Similarly, we have what is called an upper triangular matrix. This is a square matrix with zeros below the main diagonal. So like 1, 2, 3, 0, 4, 5, 0, 0, 6. Now I have my main diagonal, and everything below that is a 0. So if I draw through the entries that do not have to be 0, I have this upper triangle. We'll now discuss the algorithm that gives us these LU factorizations. The first step is to reduce A to a row echelon form by adding multiples of rows to rows below it. This is going to really restrict the row operations I can do. I cannot switch 2 rows, and I cannot multiply a row through by a number. All I can do is multiply a row by a number and add it to a row below that one. So essentially, I'm not going to try to get the 1s in our pivot positions. I'm just going to try to get the 0s below those leading entries. The second step is to place entries in our matrix L such that the same sequence of row operations we did in the first step would reduce the matrix L to the identity. And we'll do a couple examples demonstrating this process. Here is our first matrix that we'll start with. And essentially what we do is we start by leaving the first row completely alone the way it is. After all we can do is add a multiple of one row to a row below it, so there's nothing we can do to change this since there isn't a row above it. To get a 0 in the second row, we would need to do 2 row 1 plus row 2, because 2 times 2 is 4, minus 4 is 0. That would also give us 8 minus 5, which is 3, negative 2 plus 3, which is 1, 10 minus 8 is 2, and negative 4 plus 1 is negative 3. To get a 0 in the next spot, we would subtract negative row 1 plus row 2. Negative 2 plus 2 is 0. Negative 4 minus 5 is negative 9. 1 minus 4 is negative 3. Negative 5 plus 1 is negative 4. And then 2 plus 8 is 10. For the last row, I would do 3 row 1 plus row 2. That would give me 6 minus 6 is 0. 12 plus 0 is 12. Negative 3 plus 7 is 4. Positive 15 minus 3 is 12. And then negative 6 plus 1 is negative 5. Now that we've done that, not only is our first row not going to change, but we now have our second row set as well. So now I'm going to try to get zeros below this 3. The first one would come from doing 3 row 2 plus row 3 to get 9 minus 9 is 0, 3 minus 3 is 0, 6 minus 4 is 2, and then negative 9 plus 10 is 1. For the last one, I would do negative 4 row 2 plus row 4 to get negative 12 plus 12, negative 4 plus 4. I would have negative 8 plus 12 is 4, and then positive 12 minus 5 is 7. Now that I've done that, my first row is not going to change. My second row is not going to change. And my third row is not going to change. And now I'll try to get the 0 below the 2. So negative 2, row 3, plus row 4 would give me negative 4 plus 4 is 0, and negative 2 plus 1 is 5. And this matrix here is our matrix U. To find L, in this case, L would be 4 by 4 because it's determined by the number of rows in the original matrix. It's lower triangular with 1s on the diagonal, so we can already fill in part of it. And now we need the same sequence of row operations we just used to give us the identity if we apply them to L. So essentially, the first thing I did was 2 row 1 plus row 2, so I'm going to make this a minus 2. I did negative row 1 plus row 3, so I'm going to make this a plus 1. I then did 3 row 1 plus row 4, so a minus 3. Essentially, I'm just going to change the signs. The next thing I did was 3 row 2 plus row 3, so make this a negative 3. I then did a negative 4 row 2 plus row 4, so I'll make it a positive 4. Finally, the last operation I did was negative 2 row 3 plus row 4, so this should be a positive 2. And now we have our decomposition. Let's try it again here. Once again, our first row is set, and we need to get zeros underneath this 2. I can get the first one by doing negative 2 row 1 plus row 2 to get negative 4 plus 4. That would then be positive 6 minus 6. And then negative 14 plus 5, which is negative 9. To get the last 0, I would just add these 2 rows. Negative 3 plus 9 is 6, and 7 plus 1 is 8. And at this point, we're going to stop. In order to get my pivot in the correct spot, I would need to switch the second and third rows, but that is not an allowable row operation. So here, there is no LU factorization. Just like not all polynomials can be factored, not all matrices can be factored either.